Hi everyone, welcome to this M2D2 talk. Our speaker today is Christopher Beckham, who is a PhD candidate at Milan, supervised by Prof. Christopher Pal. His current research interest lies in model-based optimization, generative modeling, and continual learning. He is also currently a visiting researcher at ServiceNow Research. Thank you so much, Christopher, for accepting to present this work today. It was very last minute because we had a cancellation and you were very kind enough to accept this and to jump in. So thank you so much for that. And yeah, looking forward to the talk.
Oh, cool. Yeah, no worries. Well, thanks for being accommodating at the very last minute. So just before I start, so can everyone hear me clearly? I just want to make sure that's all good.
Yes.
Okay, great. Okay, so yeah, this is a sort of talk I'm giving. We just put it on archive, but still it's a bit preliminary. So it's only about 25 slides. I don't expect to take up the full hour. There might be some time at the end for discussion. And the way I sort of do these presentations is that, if you have a question, you can raise your hand or button. I do things sort of a bit more informally, so that's just how I do things. But sort of without further ado, I'll get started. Okay. Okay, so yeah, this is the paper. And so in model-based optimization, what we want to do is we want to learn a model of some unknown objective function f of x, right? It's a black box, it's some real-world function, and f of x is some measure of the desirability of x, right? So it's you can think of it as a continuous function. And X here could be it could be a design for any type of problem, right? It could be a protein, it could be a robot, it could be a neural network, and maybe in the case of proteins, f of x would be like the binding affinity, like maybe yes, no. I'll post that archive link at the end here. I'm just looking at the chat. So yeah, like here, f of x is let's see, be the binding affinity of a protein. Maybe for a robot, it's the running speed. Maybe for a neural network design, it's the accuracy. And so maybe for neural networks, X is like the specification of an architecture, how many layers, what's the connectivity pattern, and so forth. But yeah, it's f of x is like the ground truth. It's like the universe. We don't know it. We usually don't have it, but we want to model it. Right. And yeah, so this here, when I write it as f of x without any type of subscripts or anything, then basically this is the ground truth oracle. So just keep that in mind. So model-based optimization can be what we call offline or online. And an online model-based optimization, it's a bit more complicated in the sense that there's like an active learning loop going on, but we won't be considering that here. We'll just be doing offline model-based optimization. And an offline, I was jumping ahead. And offline, yeah, we cannot query the ground truth during training, right? And by query the ground truth, we mean like executing the real world function, right? So, if we're talking about proteins, right? If we design some new kind of protein, well, then executing f of x would be like, going to the lab, synthesizing the protein and then, sticking it in a test tube. So we mean like executing this real world process. And in the online form, we kind of assume that there's this feedback loop where, during training, we can sort of like, have a human in the loop to kind of, get more labels, but we're not going to assume that here. It's just going to be offline where we just have a data set of inputs and outputs. All right. And so typically in these MBO problems, right, you can think of the distribution of Y. So Y is the output of f of x. It's usually like, some skewed, some type of Pareto distribution where, you have, since you want to maximize f of x, as you sort of move along the right, you actually have less candidates here, right? And this is the whole point of MBO, is that we have a lot of candidates, a lot of inputs that are low scoring, but really we want to extrapolate. We want to go into this regime where there's not so many examples, but the problem is that it is severely underrepresented. And an offline MBO, like this might be your data set, and you've got sort of like, you can't query the ground truth. So it's just good to keep that in mind. And so, the most naive approach in MBO is to do this thing called, gradient ascent, right? You have this f of x that, maybe you want to find an x that's the argmax of this function, but we don't have f of x. And so you can approximate it with this f theta of x, right? So you can just train a regression model on your training set. And so this f theta here, we call this an approximate oracle because it's a classifier that we train that's, another neural network. And then, we can do sort of gradient ascent, right? We can back propagate through this. But that can be kind of problematic, right? Approximate oracles in general are problematic. The first reason is that f of x can actually overestimate the score of a candidate, right? Maybe you synthesize a protein and the approximate oracle says that it has a very high score, but really it's a low score, right? And if you're familiar with like the adversarial example literature, then you probably are familiar with this. You kind of know where I'm getting at. But in the second case, right, f of x can assign a non-zero score to an invalid candidate. And so I think I explained what invalid is in a later slide, but we just we'll just assume that invalid just means that it's not possible to synthesize it. It's not valid, right? So in the case of, let's say, a chemical compound, right, we know that certain atoms can't bind to certain other atoms and certain structures are not possible. And so in the case of chemistry, an invalid candidate would be like, here's like a chemical compound that I want you to synthesize, but it's like, no, it's not possible. And so we know that f of x can do this, right? Because it's a discriminative model, and discriminative models are very vulnerable to these sorts of things. If you want to get more technical, right, for a lot of problems, we have this thing called the manifold hypothesis, right? It's not the case for all data sets, but for most data sets in deep learning, we have the situation where the space of valid inputs actually lies on a lower dimensional manifold. And so we know this for images, right? Like if you can easily produce adversarial examples on an ImageNet classifier, and have some, salt and pepper Gaussian noise image, assign high confidence to a class. So it's the same thing here, right? So basically, discriminative models can be very flaky. And so, to kind of resolve these issues, well, I'd say that the first problem, which is overestimation, I mean, that can be mitigated through rigorization, right? So, if you train this approximate oracle, use whatever rigorization you want, weight decay, other things, other rigorizers. But really, I want to focus on two, which is that, this whole problem of scoring invalid examples, you can actually mitigate this through generative modeling, right? And this is precisely what generative modeling is for. So I kind of propose, and I'm not the first to propose, generative modeling for MBO, but I'd like to think I've kind of sort of develop some ideas that might be useful, is that I feel like, one should really be looking at MBO through a generative modeling lens, not a discriminative model lens. And so, you can think about, you have this, I don't know, you have this chemical compound, and maybe you run it through your approximate oracle f theta of x, and you're going to get a score, right? And, we assume that the score can be anywhere from 0 to infinity, where infinity is like the best possible compound and 0 is the worst. But it's good to kind of think about it in a more probabilistic manner. Like f of x is a, it is, you could say there is a relationship between f of x and p of y given x, right? We can think of f of x as, let's say, parameterizing the mean of a distribution. So obviously these are not the same, but it's good to sort of think about things probabilistically. So f of x, does parameterize as p of y given x. And even the ground truth oracle, there is this notion of a p of y given x, because the ground truth oracle can also be stochastic, right? Due to sensor drift, stochasticity and sensor measurements. And so to kind of hammer this concretely, discriminative models only consider p of y given x, right? So the way you read this is that, what is the probability of y given that I have observed x? But what if x shouldn't have been observed in the first place, right? Like, what if this is some compound that is, that is just not possible, right? Like maybe you have, atoms that should not be bonding to other atoms, but that's what your model spit out, basically, right? And so really we should be considering the joint density, right? The joint model p of x and y. And we know through Bayes' rule that P of X and Y is just P of Y given X times P of X, right? And so this is really the key thing, right? Is that we want to kind of account for this overall probability of observing X. If X is not possible, like if we cannot observe X due to the laws of the universe, right, then P of X should be 0. And then this whole term becomes 0. And so, yeah, like it's kind of very important that one sort of consider the joint density instead. And also, through Bayes' rule, you can also flip them around. So it can also be P of X given Y times P of Y, but I won't complicate things for now. But I guess really, you could ask the question, when should we use generative models for MBO? And I would say that, well, to kind of be concrete, in this talk, I'll say that a generative model is actually either one of 3 things, right? It's either P of X and Y, or P of X given Y, right? So anything where there's X to the left-hand side. But just for the sake of simplicity, we'll just mainly consider the joint density. And a discriminative model is P of Y given X. Now, I guess what you have to ask yourself is, for the MBO problem that you're considering, is it possible for a candidate X to be invalid? And by invalid, like I said earlier, let's just assume we mean it's not possible to synthesize. So, a positive example of this is chemical compounds, as I said earlier, right? Certain atoms can only bond to certain other atoms in certain configurations, and so it seems that makes sense. But I'd say a negative example potentially is actually DNA strings. We know that arbitrary combinations of nucleotides are possible, right? We know that we can have any sort of arbitrary combination, adenine, thymine, guanine, and cytosine, and they could sort of be in arbitrary combinations and so forth. So maybe in this case, we don't really have this notion of there being invalid candidate. I guess it really depends on what semantic meaning you'll assign to F of X. But just for the sake of this example, I'll just say that this is actually like a negative example of this. And so, I'd say that, a generative model is very important for this, but maybe for DNA strings, it's not so important. But still, I do think that generative modeling is the way to go, because it's very easy to modify a generative model to be semi-supervised and to use unlabeled data. But I just want to kind of make this distinction. And I'll say that generative models implicitly account for invalid inputs by modeling the distribution of valid inputs, right? So it is possible to, let's say, you could imagine, training a regression model, training an F of X, and, regularizing it by saying that, like, if your data set contains invalid candidates, maybe you could add a regularizing loss to say that, F of X should be 0 for these candidates. But I do think that's hacky, right? Generative models implicitly account for this already. In principle, you don't need negative examples for a generative model, right? Because Joshua Benji raised his hand. Yes?
Yes, thanks, Chris.
Yeah.
I have a concern here. If you're in the space of molecules and you're trying to discover new molecules,
yeah,
I think we should really distinguish the chemical constraints, like, only certain atoms can bond to certain others,
yeah,
from the distribution over molecules. Because really what chemists or pharmaceutical industry is interested in is new molecules that are actually quite different from the ones that they already know. So if you were to train a generative model, say for P of X,
yeah,
it would discard the things that they're actually trying to discover, because they're doing active learning. They're trying to go outside of the realm that they already know. So
I think I'll get to that. Okay, yeah, I get what you mean. I'll kind of get to that, because I just want to clarify that, when you train a density model, like learning P of X, right, we know that sampling from that model, sampling a candidate from that model is proportional to its likelihood. We don't want to use generative models to sample likely candidates. And yes, you're right, that's the caveat. So we want to have a generative model but we want to sort of extrapolate the generative model. And so I'll kind of get to that, and I kind of more formally define it in the archive, but here I kind of simplify some things. But yes, I'll get to that. That's a good point.
All right. Great, thanks.
But yeah, but to go to this last point, right? Like I mean, generative models already do this, right? Because the density has to sum to 1, right? So by pushing up the likelihood of everything that's valid, you're pushing down the likelihood of everything else that's invalid, right? And so because there are papers that what they do is that they'll train an f of x, but then they'll regularize it and they'll treat it as an energy model. And I'm not saying you shouldn't do that because it is, classifiers are cheap to train, but I'm just saying that I don't think it's the most principled way to do it. So anyway, so let's take, for example, sampling and scoring from a joint density. Let's just assume that we have a joint density P of theta x and y. And maybe it was trained on this training set, right? So I'm just showing the distribution of y, but just imagine that for all examples in the training set where the y's are in this region, we train this density. And maybe what we want to do is that at test time, we want to, condition on a y that's in this region. And I'm kind of being fancy. I'm just assuming that we have some like fancy text generative model that can sample an ASCII representation of the molecule, or it could also be a graph. But the thing is, in order to ascertain whether this is actually what we want, we have to do a ground truth evaluation, which costs bags of money, right? Because f of x here is the ground truth process, right? So we have to we have to synthesize this, and then we have to perform some experiment. If it's like maybe the binding affinity of it, and maybe we need to do some wet lab experiments. So this is expensive, right? It could be tens of thousands of dollars to do this. And so really the question is, can we use cheap proxies to evaluate the fitness of a generated candidate? Can we use some proxy to kind of avoid doing this? And so to kind of get into sort of what I'm proposing, it's useful to do just a bit of a brief refresher on evaluating models in machine learning. I'll just say generally in machine learning, and let me just use a classifier, for example, right? We have a training set, we train a classifier, and we evaluate its accuracy. And we know that this accuracy is highly biased because we're evaluating the model on the same thing that we're training on. And so I'll say maybe we get 97.6% accuracy. And this is highly biased. And so then we kind of have this notion of a validation set, but we also do what's called model selection or hyperparameter tuning on this validation set. So we want to tweak things. Tweak the learning rate, tweak the weight decay. We want to sort of tweak certain hyperparameters so that it performs well on this validation set. And then, maybe we do this evaluation. And obviously this is going to be less biased than this, but it's actually still kind of biased depending on how much hyperparameter tuning you're doing, right? We know that this is a very long and iterative process, right? You might be spending, months in this feedback loop, right? And so, this is less biased, but essentially you're doing this, gradient descent by grad student, basically tuning parameters to kind of get an estimate here. But, you would expect that this estimate would be a bit less than this. But, also, we have, a held out test set, right? So when this process is done, well, then you would evaluate P of y given x on this test set. You would compute the accuracy over these examples, and you'd compute the likelihood. And this will be your unbiased estimate. And if I can just kind of give a mini rant, these days in deep learning, these two are the same thing. Because we're in this culture where people obsess over SOTA and people obsess over benchmarks, and a very easy way to beat someone else's SOTA is to make these the same. So if you've been hammering the test set for like, hundreds of hours, then you'll get a biased estimate. But generally, if you're not in the game of, beating people's benchmarks by 0.001%, well, this is really how you're meant to do things, right? And the key thing here is that, to perform evaluation, we don't need the ground truth itself, right? We just need samples from the ground truth, right? And this is really the principle underlying maximum likelihood, right? We just, hopefully we have lots of samples here, right? Otherwise we might get a bad estimate, but assuming that you have enough samples, that's the whole beauty behind it, right? Like we don't actually need the ground truth model because the ground truth model is the universe and we don't have the universe. And so that's really the key thing. But in MBO, it's a bit more complicated because, so I'm just modifying this diagram now to say that we have a joint density P of x and y. We have the same thing. But in this case, we have a generative model. It could be a GAN, it could be a VAE, it could be the diffusion model. You choose your choice of model. And maybe at test time we want to sample a Y that we've never seen before. And we input that to our joint model and we sample. So we need to generate and evaluate. But we don't have this. We actually need the ground truth f of x, right? Because we want to compute the likelihood of something that we have synthesized ourselves. This is something that we want to generate, right? And so it gets a bit finicky. And maybe here we compute a mean score. So maybe we generate like 100 candidates. You can maybe sample from this little distribution here and compute a mean score. So this is kind of the bottleneck. And so the difference between earlier is that we actually need the actual oracle, not just samples from it. But we'll talk about how to kind of to address that. And so really, we have this validation set, right? So we can sort of ask ourselves the question, what validation metrics correlate the best with the ground truth? And also, how do we measure extrapolation? So for the remainder of this, I'm just going to assume that we have f of x, but I am going to account for the case where we don't have it. So there's kind of two modes that you can operate in MBO, but I'd say like these are the two questions that we should be keeping on our mind. Is that is there a metric here that we can come up with that correlates well with this, and also how do we kind of like more formally define how to measure extrapolation? So maybe I'm jumping here. So I'll just before I get into it, I'll just say really there's two types of MBO data set in the literature. And the first is actually when the ground truth f of x is available. Now by available, I just mean that it's exact and we can basically run it in the code, right? So it's not some external like wet lab thing that we have to do. Like it's basically a function that we can run. And typically these are simulation data sets. So offline REL data sets, maybe you're controlling a robot or something, or also they could be very small dimensional data sets where every possible input's known. So one example is actually the transcription factor binding data set is actually a data set of length 8 DNA strings, right? And the total space of, so there's only like 65,000 possible inputs, right? Because it's 4 to the power of 8. So in this case, because the data set's actually entirely realized, the oracle is basically just a lookup table, right? It's just a hash table. And then you have this other type where the ground truth is not available. And typically these are actually hard sciences data sets, obviously. Superconductors, one of them, ChemBL, QM9. And so in that case, you actually have to train a test oracle. And so in that case, we call it an approximate oracle. And I'll get to that later on. But first, let us just consider the first case because it's kind of convenient. And so, really the question is like, how do we measure, extrapolation with a validation set? And so kind of what I'm proposing is that, if you have your data set here, this is like the entire data set that you have for MBO, you can think about that as being samples from this ground truth density, P of X and Y. And so what we can do is that, we can basically cut the data set based on some threshold gamma based on Y. And so we have a situation like this where, if this is your actual probability distribution over Y, we can impose some threshold gamma where we can say that the training samples actually come from this truncated distribution, right? So any examples whose Y's are between 0 and gamma are actually going to be in this regime, and any examples that are from gamma to Y max are going to be here, right? So we can think about the training and validation as coming from their like respective truncated distributions, basically. And so now these are not from the same distributions. And so here I'll just kind of call this the extrapolated region. And the idea is that you would train a model, P of X and Y basically only on this part. And to do validation, you need to devise some validation metric between this model and the validation set, right? Now for this talk, I won't go much. For the sake of time, I won't go into the specific validation metrics, but I just will say that it really depends on a generative model. If you're, using a generative model where you can compute likelihoods like a VAE or diffusion, well, then you can just, you could also do compute the likelihood on the validation set, but in the general case, it's not really clear, what the best metric is to kind of just measure this extrapolation. And maybe when this feedback loop is done and you've kind of done your model selection, all that sort of stuff, well, now you're going to generate samples where you sample from this extrapolated region. So we're actually going to sample from the empirical distribution over this, and we're going to sort of generate samples, and we're going to have what's called a candidate set. And from that candidate set, we can now basically compute the expected value of these samples, right, with respect to f of x. But then sort of the $1 million question is, well, the first thing we want to do is we want to sort of measure the correlation between these two. But $1 million question is like, what's the best, what's the best metric to measure extrapolation? And it could be a divergence, it could be a distance between distributions, and that's kind of the big question here. So yeah, like, I mean, one such example is, well, I guess I'll explain the procedure first. For a fixed generative model and data set, what you could do is that you could sort of enumerate many possible hyperparameters and then plot the validation metric versus the actual Oracle score. So this was an example I actually did for a GAN, and I was basically kind of using the Frichet inception distance, which is a popular metric used in GANs, and basically just ignore the green points, but essentially the orange point is these actually corresponds to the ground truth oracle. And so we're seeing that there's actually a strong negative correlation here between the two, right? So generally in GANs, you want the FID to be lower because it's measuring a distance between two distributions. And we basically see that as the FID is going down, this mean score, this mean expectation here is going up. Right, but ideally we want to do this for many types of generative models and many types of metrics. But yes, going back to what I was saying earlier, right, the main limitation is that we actually need the ground truth oracle, and it's a bit of a circular problem, right? Because I'm saying that we would like to have a validation metric that correlates well with the ground truth oracle, so we don't have to waste money. But in order to do that, you need the ground truth oracle. So it's a bit circular, and that's kind of one limitation. And so in order to kind of do these sorts of experiments, right, you either need to be operating in like small dimensional or simulated data sets. But I'd say that the other thing we could do is we could say, like, how can we modify the evaluation to accommodate when you don't have the ground truth oracle? And this is where things get a bit more interesting. And so, in this case, right, we wouldn't have f of x here. We would actually have to replace it with what's called an approximate test oracle, right? So I'm using phi here, the subscript to denote that it's approximate. And so basically, in this situation right now, you actually do need a test set, right? And so the test set would come from the same distribution as the valid set, which would come from the same distribution as this. But basically, we train this test oracle on all of this data. But I suppose that, since the test oracle is also approximate, it is hard to sort of be sure of model performance. And the reason is because it gets really flaky, right? Because this p theta of x and y, this is one approximation, but now we're measuring the performance of one approximation with another approximation. And so, it's not that you can't do this, but I'd say, like, whenever you have this approximate test oracle, you really have to take things with a grain of salt. And as I said earlier, right, discriminative models are liable to overscore examples, and they're also liable to assign non-zero scores to invalid inputs. But I do think that there is a compromise that one can make to accommodate for this. And so how can we, so I already talked about the first point, right? Obviously to mitigate this, right, it's all about regularizing the oracle, but I'd say that there is a potential way that you could mitigate this in this scenario. And I'd sort of propose that, this thing called ground truth verification. Some problems may allow for ground truth verification rather than scoring. So what do I mean by that? You can imagine that there is a function, v, so v for verify, and maybe, v of x, it's a binary function, and maybe it scores x equals 0 if x is invalid, otherwise it scores it to 1. I guess it could also be a continuous function, but I'm just going to assume that it's a simple binary function for now. And so, maybe like, this kind of reminds me a lot of, like, in computer science, right? Like, some algorithms are NP hard. Some algorithms take exponential time to compute a solution, but maybe it's actually very cheap to verify that it's a solution. And it's a kind of similar analogy here. Maybe we don't have the ground truth to score a molecule, but we can at least verify it very quickly. And so, one example of this is chemistry retrosynthesis. So I don't know if Cheng Hao was in this channel, but he's a chemist at McGill that I spoke to recently about this. And he was telling me that if X is actually an organic molecule, then you can actually run retrosynthesis to actually determine whether it's plausible to synthesize or not. And so basically, I might be jumping here, but yeah. So we were kind of talking that there's this data set called QM9. And in QM9, this is actually a data set of organic molecules, and basically this could be a target data set where we could try something like this on. But the idea is that if you have this approximate test oracle, right, what you could do is that you could actually combine it with this verifier, which is exact, right? And yep. Sorry, I can't hear you, Joshua. Is your mic muted?
Sorry, I'm a bit confused with what you're trying to do. So why can't you, if we go to the idea where you separate the training and validation set, with the validation set being only like large values of Y?
1 second.
Yeah. Yep. So you know the values of Y's for the validation set or the test set, doesn't matter.
Yeah.
So you can, and then you can also generate some X's and Y's that come from your P of XY, given that Y is supposed to be greater than gamma.
Mm-hmm.
Okay, the problem is you don't have F to know how good they really are. Is that the problem you're trying to solve?
Yeah. I mean, if we assume the worst case scenario, then so right now, right? So yeah. So let me actually just go back to this other diagram because it's a bit simpler. Yeah. So it is yes and no, right? So yeah, we assume that like it's this kind of chicken and egg problem, right? Where in the real world, evaluating this f of x is expensive here, but we're kind of for the sake of evaluation, we want to find validation metrics that correlate well with this. But sure, like, I mean, the only thing we have is that we have samples from this validation set.
Right.
So you could, so I more formally kind of define some of these things in a paper, but if P of X and Y is, let's say, a likelihood-based model like a VAE or a diffusion model, you could evaluate the likelihood
That's
of
what I was
samples
thinking.
in here. But that's not the same as, let's say,
No, but
synthesizing
you could,
a novel.
Yeah, no, you're right. You're right. But you could check that P of XY is consistent with the validation data. For example, you could check whether the Y's that I think go with the X's in the validation set are indeed greater than gamma.
Yes, that's correct. So yeah, like basically, like in the preprint, right, I kind of talk about it really depends on what generative model we're using, and so in that paper I was kind of considering the worst case scenario, which was a GAN, but in the case of a likelihood based model, then yes, you can actually you can just compute the forward KL divergence between this and basically this here exactly right, and so yeah, like exactly right, like if this can explain these examples, as in this assigns high likelihood to these, then yes. But I think like this is kind of like an artificial thing that we're doing just for evaluation, right? Because remember that in the real world, after we've done all of this, we're actually going to retrain on all of this, right? So we're going to retrain on all of our data, and now we don't have a test set anymore, right? So
no, but we want even larger. But the thing is, we want even larger Y's, or we want maybe other X's that have a large Y.
Exactly. So in the real world, so like when we retrain this, right, basically now we want a condition on Y's that are actually beyond this region. So exactly. So it's kind of like, I find that like, it's sometimes really hard to think about all this unless you have like all these diagrams, but sure, right, like you can sort of modify this diagram to say like, when this is all said and done, now we retrain on everything, and so like, there are sort of ways to, when you've retrained the model on all the data, now the question is, well, what Y should I condition on? And there are kind of ways to address that, right? you can look at exponentially tilted densities, which basically allow you to trade off between risk and reward, but I won't get into that. But yeah, so anyways, you could do the same thing here, right? Like if you had a VAE, right, maybe this wouldn't be the FID, it would be like the forward K divergence. But like I said, the $1 million question is like, it's not clear to me what metric or divergence or distance is best to measure this kind of extrapolation, right? Because again, these come from different distributions.
All right, thanks.
Yeah, no problem. But yes, thanks for bringing that up. So anyways, like I'm saying, right, so maybe like, in this case, right, if phi is approximate, right, but if we could multiply it by this verification and we just assume that this is like a ground truth verifier, then basically this is going to be 0, right, for any x that's invalid. And so like what I'm proposing here is that like if you have a verifier, you should kind of fold it in and just multiply it with the approximate test article. And sort of what I was saying is that I don't know if there are any papers that there's. I was speaking to Cheng Hao, and I think he was doing something similar. But I think QM9 would be a great data set to do a proof of concept here, because it's basically organic molecules, and it is very kind of MBO appropriate in the sense that there are different continuous attributes that you can actually use for Y. But really, that's really what I'm saying here is that, in this situation, you have to be very mindful that, this is an approximation and this is an approximation. So, you kind of have to take everything with a grain of salt. Anyways, I haven't talked so much about related work, but I will say that, in the preprint, I do kind of relate this to a lot of other papers. Our sort of work builds our evaluation kind of builds upon design bench, but it's also kind of incompatible with it because design bench doesn't actually give you a validation set. But this is sort of like a framework that our code is sort of built on top of. And sort of there are a lot of existing models. So conservative objective models is basically a regression model that they use. They basically train a regression model like it's an energy function. There's model inversion networks, which is basically just GANs for MBO. There's also CBAS. And so basically I've sort of, spent a lot of time relating sort of our model formulation, our evaluation framework to these models. And obviously, going back to what Joshua was saying, right, like it really depends on the generative model that you're using, right? If you're using likelihood-based models, well then, one easy metric is actually just compute the likelihood and validation set. But in the general case, right, if you're using a GAN, well, then you're not going to be able to compute likelihoods. You're going to have to compute other things. And so, we did some proof of concept experiments basically on a modified version of this transcription factor binding data set. But really, there's a lot more work to do. This needs to be evaluated for different types of models. Diffusion models are very sexy and for good reason. And so, some work I'll be doing soon is actually, training up diffusion models and seeing how they perform. But also I haven't written it here, but I like I said earlier, there's a lot of sort of MBO data sets, that are kind of in the hard sciences. And I think a good sort of way forward is to kind of like, see if we can, consider problems where you can actually have this verifier, right? If you're considering problems where the ground truth oracle is known, then I think that we need really good simulated data sets, like really good challenging simulated data sets, so we can take those findings and actually apply them to problems where you don't have the ground truth oracle. So no matter which like MBO data set you're working on, whether it's one or the other, I think there's a lot of work to be done. So yeah, the conclusion is that MBO evaluation is considerably more difficult than what I would call regular machine learning, because you're not evaluating the likelihood of test samples. You're actually creating your own test samples, and you don't know the labels of them. And we kind of have proposed this evaluation framework that really asks this fundamental questions, like what validation metrics correlate well with the ground truth, where we assume that these validation metrics are cheap to compute so that we can save money. And sort of we discussed two cases, right? Like when the oracle is readily available versus when it's not. Norm, so what does it mean MBO? So MBO is model-based, it's just model-based optimization. You just have some function Yeah, so some function f of x that you want to approximate, but you want to sample from it. And I just will say that MBO is very closely related to offline reinforcement learning as well. In offline reinforcement learning, f of x is the reward function, right? So offline RL is just like, instead of synthesizing an input, you're synthesizing a policy. So it's very similar. If you're, in case you're from like the reinforcement learning world. And so yeah, I said basically, you know, yeah, basically there's kind of two cases. If the oracle is available, then you could do things one way, but if the oracle is not readily and cheaply available, then you have to do things another way. And so yeah, this is still ongoing work, but the code will be up soon. The preprint came out this morning, which sort of kind of more formalizes this. Formalizes this more theoretically. And you know, we kind of like make these connections with other works. But yeah, it's more theoretical, but I think it's worth a read if you know, if you're into that kind of stuff. So that's it. Thanks. Sorry, Joshua, did you raise your hand?
Yes.
Yeah.
I'd like to go back to some of the things you talked about at the beginning. You don't need to change your slides.
Yeah.
Regarding the sort of what happens when you train a model that you'd like to optimize over, the MBO thing.
Yeah.
That, you know, how the optimizer can zoom in on the sort of the wrong parts easily.
I will go back because I think it's good to show this. Yeah. Sorry,
that's
continue.
fine. And you said, okay, well, maybe we can solve that with regularization. I'm not convinced, by the way. So let me try to suggest something more powerful than regularization. I mean, regularization will prevent you from doing like really, really stupid things, like a huge value map or something. But that's about it. You can still put a large value where it shouldn't, and do it with high confidence, which is the problem.
Yeah.
If you think probabilistically. And
yeah, sorry, continue.
No, go ahead.
No, so I will say, just to elaborate on that. So really what I was actually referring to in that sense was, so if you look at the conservative objective models paper, right, what they do is that, actually no, it's the follow-up to that, which is from Kumar. They're doing conservative objective models for hardware design, and so in their paper they were saying, well, and again, like I agree this is hacky, but they were saying, like, you know, if you have a data set of invalid candidates, right? If you have like a big bag of negative examples, we can just impose an extra, you know, regularizer loss and say that, you know, we should force that f of x equals 0 for any of the negative examples. And so it reminds me a lot of like training an energy model, right? Because you want to increase the likelihood, or let's say minimize the energy of the stuff that's real, and then maximize the energy of the stuff that's not real. And I was thinking, well, you can do that. But in generative modeling, like when you're training a density, you don't have to do this because there's this constraint that it integrates to 1, right? You know, even if you don't have the actual density, right? Because for most generative models, you don't have it apart from, let's say, flow-based models. But yeah, I just wanted to kind of expound on that.
But okay. So the point I'm trying to make is a bit different. So I'm trying to see. So if you think about like model-based RL, for example, you have this issue that the policy will zoom in on where the model thinks that there's high reward, even though it's just garbage, right?
Yeah.
And there's some places where the model is kind of overconfident and then wrong, and so you will get that. And I think that's one of the main reasons why model-based RL hasn't been working up to now. So I think there's an obvious solution in principle, which is to be Bayesian about the model, right? So if your model has, if you want, calibrated probabilities in the sense that it takes into account its own epistemic uncertainty, then it can't be confidently wrong. I mean, the worst thing that's going to happen is that it just doesn't know what the answer is, and when you generate an X, you will also kind of know that, well, this is not at all guaranteed to be good, right? So maybe you don't want to, if you want to be decision optimal and there's a price to doing that experiment, you might not want to do it. So yeah, I think that this whole thing of model-based optimization could get a big improvement if we make progress on models that are Bayesian. Of course, we don't know how to do that efficiently, but okay, I do using GFlowNets, of course.
Yeah. So I was actually going to say, like, like it's kind of convenient because I was speaking to Emmanuel about this, and I think that there is an opportunity to actually use. Sorry, I'll answer your question just in a second because I see that you wrote something, but I'll say that I was speaking to him about that, and I think GFlowNets could be used for some of these problems where you're actually sampling molecules directly. But I remember that Emmanuel was telling me that there is this interesting property of GFlowNets that could be interesting here, that I think the joint density P of X and Y could be proportional to the score F of X. We spoke about this a few weeks ago, but I do think that there is actually room for it. And I didn't have time to mention this in the preprint, but because GFlowNets do comprise, because they are a new class of generative model, that's something that, yeah, I don't have time, but I do think that there could be some interesting work that could be done in that.
Well,
right?
so the thing that we've exploited mostly in our papers is the diversity of samples. So if you want to generate new candidates for either drugs or for programs, I mean, like our neural net architectures, you're not to generate just one candidate, you're going to generate a bunch, and you're going to be able to eventually evaluate that bunch. And you want that bunch to be diverse. And GFlowNet is going to do that for you because they want to sample from all the modes of the, of the reward function, or your scoring function, your F or whatever. And that's in addition to the thing about Bayesian. I mean, the two are connected, but these are two different points.
Yeah. Cool, thanks. Okay, also, Noam, any thoughts on continual learning? Continuous learning. Yeah, I guess continuous learning is I guess the way I think about, I'm just kind of like being hand wavy. I just want to make sure that like sort of get what you mean. I guess in continual learning, I guess the issue is that there's always, you kind of assume that the distribution is always drifting. And in this case, we don't really, I guess in this case, it's more of like a few shot thing. Like I think few shot is, let me just go forward here. Yeah, I'm not sure. Like I think this would be like more kind of similar to a few shot setting, because in a few shot setting, you kind of have this notion of like there being like a source and a target distribution. But I think continual learning is a bit more, yeah, it's a bit more ambitious in that I think it's kind of assumed that just over the course of time that your distribution is going to keep changing, it's going to keep drifting. And I mean, is that the case for MBO? I'm not sure, but I think that, you know, it depends on how you define it. I guess you could call this an instance of continual learning, but I think I'd classify this more of, this is more about distribution shift. I mean, but typically when people think of distribution shift, they think of like, yeah, the distribution is drifting because, you know, now like Twitter used to be like this, and now Elon Musk bought Twitter. And so now the distribution has changed because everyone's talking about, you know, how Twitter might implode. But this is kind of a special type of distribution shift where, you know, you're actually intentionally shifting the distribution, right? You're intentionally wanting to sample candidates that score higher than what you see in the training set. So so that's my very like rough and maybe not precise answer. I just see more of this as like yeah, extrapolation or out of distribution. But please let me know if I missed if I missed that. Or if you mean continual learning methods, sure, you could apply, you could look at the literature and combine the see what's happening. But yeah, cool. Okay, thanks.
Any more questions? I think there was a question by Harry in the chat.
Oh yeah.
Should we consider X when we define the extrapolated region? Ideally, both X and Y should be different from the majority of sample in the training set.
Yeah, so it actually is. So yeah, sorry, it's a bit confused. So like in this plot here, I'm only showing the distribution over Y, but like because essentially D valid is basically all of the X's whose Y's are greater than gamma, right? And we know that P of X and Y's is a joint density. Like they're not like they're not, X and Y are not independent, they're dependent. So to answer your question, like, yes, like X is also the extrapolated region. Yeah. So yeah, even though I'm showing the probability distribution of Y, really what I should have shown is like like a contour plot maybe, and showing like, in this contour plot, there's like X's that have Y's that are greater than gamma. Harry said, GFlow nets aims at diversity, but those diverse samples are still from the distribution of the original data set. I mean, maybe this could be a question for Joshua, but I will say, like, in this framework, right, like, essentially, like, even though the generative model is only being trained on the training set, we're basically selecting the model that actually performs the best on the validation set, right? So like, it's this interesting, we're not training on the validation set directly, but we are tuning the model to explain this well. And so this is kind of like, what we use to assume that, well, not assume, we're assuming that if this explains the validation set well, and by explain it well, I mean assign high likelihood to these examples, then we're also assuming that, actually, no, it's not an assumption, it's a truth, right? So if this assigns high likelihood to these examples, then it's also going to be likely to sample those, right? Because the probability that you sample something is proportional to its likelihood, right? So yeah, so if this is high likelihood, it's going to sample candidates that are like this, but you just hope that it will actually, like, generalize, right? We don't want to memorize the validation set, which I suppose could happen if you've been hyperparameter tuning for like millions of GPU hours, but you would hope that you could actually generate novel examples in this regime. But maybe I can defer that question to Joshua, since also that's specific to GFlow nets. If I don't know if Joshua's still here, but
yeah, I think he's about
he bobbed out. he failed. But yeah, yeah. But anyways, I hope that was